Educational Communications and this station present Environmental Directions with Nancy Perlman. On this series, we explore the effects of human influence on the Earth's ecosystems and discuss solutions to environmental problems which affect the quality of life on this planet. Environmental Directions gives you the kind of information you need to help you participate in decisions impacting your community, the nation, and the world. Now, here's your host, Nancy Perlman.
Hello. I'm here at the California State University at Los Angeles. With me is Dr. Frank Gomez, who is a professor of chemistry in the Department of Chemistry and Biochemistry in the College of Natural and Social Sciences. He also serves as Research Development Liaison here at Cal State L.A. He's published hundreds of technical articles and 2 books on his research. He received the CSU PERB Biotechnology Faculty Research Award. He's been a former member of the Montebello Unified School District's Board of Education and was on the Montebello City Council. He currently serves on the Board of Trustees of Don Bosco Technical Institute and of the Presbyterian Intercommunity Hospital. And he is on the Board of Directors of the Southern California Conferences for Undergraduate Research. Welcome. It's a pleasure to have you with us.
Welcome, Nancy. How are you?
I am fascinated to find out more about your research and have you explain something that most of us are probably using but don't have any idea what they really are. And this is something called microfluidics?
Yes, microfluidics uses very small quantities of material, small volumes of sample. So let's look, for example, at your hair. The width of your hair is approximately 70 microns in diameter. So if you would look at it under a microscope, you'd be able to see the thickness of it. But using just your eyes, it's very difficult to see the thickness of it. If, on the other hand, you were able to create a microfluidic chip, you'd be able to place that individual hair in a channel. So think of a trough where a horse has to drink water. But think of putting a cap on the trough and putting an inlet and outlet on either side of the trough where water can flow in and water can flow out. But miniaturize it so that it would be the width of your hair. That would be a very simple microfluidic channel. So what we have done and what other researchers are doing now is utilizing this basic premise of microfluidics to look at environmental issues, defense-related issues, bioanalysis, for example, and one of our fortes, fuel cells, as well as point-of-care diagnostics.
Apparently, we need these little portable devices. We need this in portable devices like cell phones and computers, this sort of micropower. Is that what it is?
A lot of the basis for your cell phones, for your laptops, for diagnostics, for example, is based on early technology that was used in the transistor field. So if you would open up an early radio, you'd see how a lot of the wires are placed and how a lot of the electrodes and how the gold was placed in some of these basic old radios. You could think of that same type of schematic as how microfluidics is placed also. And so we have built on that early technology in doing the same thing in moving fluids, but very small amounts of fluids in today's world also. So our research is focused in 2 areas, which is the fuel cell area as well as in the diagnostic area, and we're trying to marry both of those 2 together.
But apparently there are different kinds of fuel cells, the methanol fuel cell versus the paper-based microfluidic formate fuel cells.
Yes, so methanol, just like what one can get from corn, for example, can be utilized using a microfluidic type of chip. There's a lot of general chemistry that goes on in just what we call redox reactions, where you have an oxidation and a reduction that occurs. And when that redox reaction occurs, you generate electrons. And those electrons are actually can be transformed to energy. And that energy then, you can use that to operate some sort of device. Now that energy that's generated from a microfluidic fuel cell may not operate your car, it may not operate your refrigerator, but what it can operate is a small device, for example, your phone, or a diagnostic device. Take, for example, the home pregnancy test or a glucometer, much in the same way that maybe your parents or your grandparents, for example, may need to test their insulin levels at home or at the medical office.
What does this actually look like?
One can think of a small device that looks like a Y-shaped in the case of a paper microfluidic fuel cell. So if you can imagine a device that is about 1.5 inches long.
And you're showing me a little piece of paper that looks like it has a little metal surrounding it?
Yeah, so imagine you have a Y piece of paper that on either side of the ends of the Y, you have fluid that on the left you have potassium hydroxide and on the right you have formate or formic acid. And by capillary action, much in the same way as if you, for example, would spill milk on a table, you put a paper towel and the milk would be absorbed by the paper towel. By capillary action, fluids would move up into the main part of the Y. You then put electrodes on either side of the copper plates and hook that up to an instrument. By natural redox chemistry, with the KOH and the formic acid, you would have a redox reaction occur. That redox is actually electrons that are being created by the redox reaction, and those electrons then could eventually operate, if sufficient enough, to operate a small device.
When these microfluidics are put into some technology, whether or not it's computer or cell phone, what does it actually do that we are not getting now?
The fuel cells provide energy, and that energy can be converted to a mechanical form of energy. And it's that mechanical form of energy, if you have enough of it, that can operate and do some sort of action.
And so this is really more energy efficient than our current plug into the wall and burn some carbon.
It can be, it's cost effective, and it's certainly much more environmentally friendly.
This new technology is more energy efficient and less polluting than what we're currently using. It can replace the battery?
Yes, that is true. The electrons that are provided and are created during the redox reaction will be that source of energy. So instead of having the need in these, for example, point-of-care diagnostics of a battery, you would instead have the energy produced from the redox reaction, the electrons, which would then displace the need for the battery. As you know, many of these batteries end up being as waste. And what happens, these batteries decompose, the heavy metals go into the water, eventually into the water stream. Fish eventually swim in the water. They may drink the water. We eventually eat the fish. And eventually those metals end up going into our bodies.
So I'm looking at these. Are they being manufactured on a large-scale basis? What's the difference in what you're researching versus what is already out there on the market?
Paper microfluidics only started about 7 to 8 years ago, and microfluidic fuel cell paper microfluidics has only been over the past year or so. And so these Y-shaped fuel cells are actually manufactured in our laboratories. The great thing about these chips is that they are made of paper, chromatography paper. They are easy to reproduce. Students can reproduce them just using a printer, for example, and they're very cost effective, and they do not utilize that much material. In the next half year or so, we should be able to couple these to a diagnostic device, for example, to quantitate glucose in blood.
So as you're developing this, you see a lot of potential in a lot of fields, in areas from the biological realm, chemical, agricultural, medicinal. Give us some examples of how this is going to work in these different sectors and how it's going to help the environment.
We see one area that it should have great impact. There's certainly a lot of areas on the earth that man's use of chemicals has been deleterious, and we feel that there are need for the development of techniques that can quantify just how dangerous some of those chemicals have been to the environment. There are some areas of the third world, though, that do not have the wherewithal to purchase analytical methodologies and techniques, unlike, say, the United States. Paper microfluidics, being so inexpensive, may be one of those areas.
I'm beginning to see why you got the C Superb Biotechnology Faculty Research Award. This is really innovative and new, but so critical because we need these kinds of devices for operating long periods without recharging. We need the micropower. We need to do this testing that you're talking about of other kinds of needs. I mean, there are a lot of global energy needs. Is that where it is, or is it in testing of the quality of our water and air?
We believe that the environmental area is just one area. We believe another huge sector could be in the point of care diagnostic one, as well as in the military. Let's take, for example, the point of care diagnostic sector. The amount of power that's needed in, for example, the pregnancy test or the glucometer is in the milliamperage area. And the amount of milliamps that we obtain using these paper microfluidics is in that range. So our goal right now is to couple the fuel cells, may they be in series or they may be in parallel, such that when they eventually provide sufficient power, to then couple them to a diagnostic device and then eventually commercialize that. So we're just not thinking a small time with a glucometer and the pregnancy test, but the whole myriad of other tests that are done when one goes to the doctors to run a blood panel: uric acid, creatinine, a PSA, sodium, potassium, you name it, and such that it would save time and energy and cost so that patients do not have to go to the doctors, but are going to be able to do all of these tests at home and obtain their results ASAP, not having to worry about obtaining their results from their doctors.
And you do see the need for improvements in medical testing because you serve on boards of different technical institutes and hospitals, but you're also on the board of directors of the Southern California Conferences for Undergraduate Research. So is this something that someone working toward a BS can actually be studying, or is it really more graduate work and postgraduate?
I have my students that are in the baccalaureate programs, in the master's programs, and even when I have high school students during the summer actually make these Y-shaped chips also work on this research. So I found if you're 16 years old or 20 years old or 24 years old, the research is appropriate at all those ages. So I find that it's apropos for them. They learn the foundations of chemistry, they learn electrochemistry, they learn some engineering, they learn some bioengineering and some biology, and so it gives them a really step up when they go out and look for a job upon graduation, as well as being very competitive for graduate schools and professional schools.
For somebody like me, I will just be very thankful that this kind of new technology will be employed to improve testing and other environmental conditions. What do you see as the most effective use to protect our environment?
I think that would be several-fold. People need to conserve, people need to recycle, people need to understand that they need to learn to live for those that come after us, and to be very cognizant that the world is finite, and we want that finite ability to last a lot longer after we're all gone, and to really care about the natural resources that we have here on Earth.
I'm finding it very interesting to learn about these new technologies that you're researching and how they can be incorporated into the everyday world and hopefully will be a benefit to all of us. I want to thank you so very much for doing that research and working with students to improve the quality of our environment, and thank you for being my guest.
It's been all my pleasure.
I have been speaking with Dr. Frank Gomez, who is a professor of chemistry in the Department of Chemistry and Biochemistry in the College of Natural and Social Sciences at California State University, Los Angeles. We'll be back in a moment with more ecological issues.
Environmental Directions with Nancy Perlman continues with further discussion of the world's critical ecological issues. For more information, you may call 310-559-9160 or go to www.ecoprojects.org.